Hi everybody and welcome to a bonus lecture for Phil 2002 Logic, How to Defeat Your Foes with Reasoning. This bonus lecture is on models for monadic predicate logic. What I'm going to do is I'm just going to take a couple of models, work through some sentences and show you how to engage in the kind of reasoning that will enable you to evaluate a sentence inside monadic predicate logic against a model, no matter how complex the model and no matter how complex the sentence. I'm going to start with some simple cases and then I'm just going to gradually dial up the complexity so that we can see how this is going to extend to more complicated situations and more complicated cases. Okay, the very first thing to understand with monadic predicate logic models and when you're evaluating sentences against a model is that there's really two ways to do this. The first way to do it is a kind of rough and ready eyeballing method. So what you can do is you can look at the model, look at the sentences, try to work out what the sentence is saying, and then by working out what the sentence is saying, read that into the model to see if the sentence is true. The rough and ready sort of eyeballing type model is good if you can get your head around it. If you can get the ability to do this in a really accurate and fast way, then you'll be able to deal with a larger number of models in a shorter period of time. However, if you find it difficult to do that, or if you find that the model is too complex or the sentence is too complex to deal with in that way, then you'll need the slower, more complicated method. I'm going to focus on the slower, more complicated method that enables you to deal with a model no matter how complex, a sentence no matter how complex, without having to sort of eyeball the sentence or eyeball the model. And I'm going to show you how to generalize it to from sort of simple models to complex situations and complex models. Okay, so let's start by getting up a model, and I'll just make up a sentence and evaluate it against the model. I'm going to start with a very, very simple model. Remember, models have three things. They have a domain of objects, they have extensions for any predicates, and they have names assigned to objects if there are any names inside the sentence. So let's start with a sentence and a model. So here's the model. I'm just going to have one object inside the domain, and I'm just going to have a single predicate which has got that one object in it, and then I'm going to have a single name which names that one object, right? It's a very simple model. Now I'm going to look at a sentence which looks something like this. And I'm going to try and work out how to evaluate this type of sentence. Now the key part of the sort of long, complicated way of evaluating this type of sentence is that you have to look at all of the possible combinations where those combinations are directly related to your variables that you have in your sentence and the number of objects that you have in your domain. So if you have a look at the variables here, we've got an x and we've got a y, and we've got one object in the domain. What that means is that there's exactly one thing that x could be, and there's exactly one thing that y could be. X could be 1 and y could be 1. There's nothing else for them to be because we've only got one object inside the domain. So in this case, we've only got sort of one combination that we have to check with respect to the values for x and the values for y. If we had more objects inside the domain, we'd have to check more combinations, and I'll show you in a minute what happens when we add objects to the domain. But first of all, I just want to show you the basic method for dealing with this kind of sentence when there's just one object. Because if you can do it in the basic case, if you can do it in the one object case, then the same thing is really applicable to more complex cases. You're not doing anything differently, you're just adding more options, more combinations to chew through. Okay, so here's what we do. We start by putting down all of the possible values for x. Now there's only one possible value for x, x can equal 1, and that's it. And then, following that, we put down all of the possible values for y. Y can equal just one thing because there's only one object in the domain, so there's only one value for y. And now, what we do is we take our sentence up here and we imagine that those values are being replaced in for the variables that we have in that sentence. And what I'm going to do is I'm just going to put in parentheses, a little subscript with the number that I've set for x and the number that I've set for y into the places where the variables would be. So where there was an x, I've now put a little 1, which is representing the idea that x equals 1, and so I'm imagining in this situation that x equals 1. Similarly, over here I put a little 1 where there used to be a y, and that's because I'm imagining that y equals 1, and so I'm putting that into this situation. And now what I do is I evaluate this conditional under this kind of assumption. So given that x equals 1 and y equals 1, is this conditional statement here true? Now to evaluate this, I just do it the normal way that I evaluate conditionals in predicate logic. So what I do first of all is I check to see whether 1 really is inside the extension of A. Because what this is saying is, assume x equals 1 is 1 inside the extension of A. And because it is, I know that the antecedent, the thing on the left of this conditional, is true. And now I go over here and I check to see, is 1 inside the extension of A? Because remember, y equals 1, and that's what we've set this part of the sentence to. And 1 is inside the extension of A, and so I know that this is true. And now I just use the truth table semantics to work out the value for the conditional. And I know that the conditional itself is true because both sides are true, and the conditional is always true when both sides are true. Okay, so now what I've got is I've tested for every value of x and every value for y, this particular conditional statement. What I need to do now is relate this back to this sentence up here. How do I work out whether or not this sentence is true given this kind of evaluation? Well, let's try and work out what it would take for this sentence to be true. For this sentence to be true, it has to be the case that for every value of x and for every value of y, if x is in the extension for A, then y is in the extension for A. Now the key thing to note here is that what I have to do to make this claim true is I have to make this conditional relationship between A and itself here true for every value of x and every value of y. And that means every possible value for x and y based on the domain of objects. Which is to say that no matter what I can put in for x and y, this thing over here comes out true. Because there's only one possible value for x and one possible value for y, there's only one situation to check, and I've checked this situation, and so I know that this doubly quantified sentence is true for every value of x and every value of y. No matter what I put in here, and no matter what I put in here, this conditional over here comes out true, and so I know that this entire sentence up here is true. Okay? What I'm going to do now is I'm going to look at a slightly different sentence and evaluate it against a more complicated model. So that was the case for when we've just got one object in the domain. I'm going to add a second object to the domain, and now I'm going to look at a sentence that is a little bit different to the one that we've just looked at. All right, so let's complexify the model. I'm going to add a 2 into my domain. So now I've got 2 objects. And I'm going to leave the extension of A as 1, but I'm going to add B, which is 2, and then I'm going to add lowercase b, which is naming 2, right? So I've dialed up the complexity of the model. And now I'm going to look at this sentence. For all x, for some y, if ax, then if and only if, sorry, for all x and for some y, ax, if and only if by. Okay? So there's 2 modifications. I've changed this second quantifier to be an existential, and I've changed this to be a biconditional, sorry, 3 changes. Change this to be an existential, change this to be a biconditional, and then change that second slot to be a second predicate, b, instead of just a again. Okay, so now how do I evaluate this? Again, what's the sentence saying? It's saying for every value of x and for some value of y, if x is in A just in case y is in B. Now, the key thing to note when I'm evaluating the sentence is I really just use the same kind of method that I use to evaluate the more simple sentence. The difference, however, is that I've got more values for x and y than I need to check. In this case, because I've now got 2 objects in my domain, for it to be true for all values of x, I have to make it the case that it's true when x equals 1 and when x equals 2. So I've got to check both of those possibilities. And because I've got a second variable y, there are 2 things that y can be. Y can be 1 or y can be 2. But I only need it to be the case for some y that it holds. Now I'm going to check it for all y so we can see how the broad process works. But at the end, when we relate the sort of checking procedure back to whether we're working out a sentence, back to when we're working out whether the sentence is true, we'll see how it matters that we've changed that to an existential quantifier. Okay, so how do we start? We start the same way that we did just before. We start by putting down all the values for x that there can be. X can equal 1 or x can equal 2, right? Because there's just 2 things in the domain. And then we look at the values for y. And we note that y can equal 1, but y can also equal 2. So we've got two possible values for x, and for each of those values for x, y can equal 2. So what we're actually doing here is we're mapping all of the possible situations that there could be. We don't know what x and y are, but we can check what they could be under every possible supposition. So we can imagine what would be the case when x equals 1 and y equals 1. We can imagine what would be the case when x equals 1 and y equals 2. We can imagine what would be the case when x equals 2 and y equals 1. And we can imagine what would be the case when x equals 2 and y equals 2. And we can then just check this statement here for each of those possible situations with respect to the domain. And that's what we're going to do. So we're going to put down the sentence, and we're going to use those little subscripted parentheses again, and we're going to put in the values for x and y. So here I've written A1 biconditional B1 because x equals 1 and y equals 1, and so I've substituted those in for that sentence. And I'm going to do that here as well, but this time because y equals 2, I'm going to put B2 down. And then for the third conditional, x equals 2, so it's going to be A with a subscripted 2, and then B with a subscripted 1, and then A with a subscripted 2, and then B with a subscripted 2 as well. All right, so I've got 4 different conditionals that I can possibly check. These are all the different values that x and y could take. And because this is a universal out here, I need it to be true for every value of x. So if I've got a universal out here, then it has to be true for every value of x. But I've got an existential in that second slot, and so it just has to be true for every value of x that there's some value of y. So what that means is that for each of these, sort of, you can think of these as each of these paths, I need one path from x in each case to hold, but it only needs to pass through one of the y's. I don't need it to be the case that it holds for both of the y's. I just need it to be the case that it holds for one of the y's, but in each case for each x. All right, so let's just compute these values, and then once we've got these values, we can feed that information back to understand what's going on with this sentence. Okay, so is 1 inside the extension of A? Yes, it is. So what I'm going to do is I'm just going to put trues wherever I see that 1 is inside the extension of A, because I know that that's true. I also know that 2 is inside the extension of B, so I'm going to put trues wherever I see that. And now I'm going to look at the case where 2 is inside the extension of A. So that's what this claim is making. 2 is not inside the extension of A, so I know this is false here, and this is false, which is to say that when x equals 2, this claim, A subscript x, where the variable equals 2, is going to be false in that situation. Similarly, when I set y to equal 1 and I go over here and I test b, I see that it's false wherever it appears. Okay? And now I use that information to compute the values of the biconditional in just the same way that I did with the conditional, namely using the truth table semantics. And what do I know about the biconditional with the truth tables? Well, I know that the biconditional is true when both sides stand together or fall together. And it's false when the two sides have differing truth values, when one side is standing and the other side is falling, or when the one side is falling and the other side is standing. So I'm going to look for cases where both sides have the same value. The second case is one of those, and so is the third case. But the first case, they've got different values, so the biconditional is false. And then in the fourth case, they've got different values, so the biconditional is false. Okay, so what does this tell me? Well, it tells me that when x equals 1 and y equals 2, this biconditional is true. It also tells me that when x equals 1 and y equals 1, the biconditional is false. It tells me down here that when x equals 2 and y equals 1, the biconditional is true, and that when x equals 2 and y equals 2, the biconditional is false. So I got those 4 pieces of information. Now, I'm going to have a look at this universal sentence with respect to this existential quantifier. What it's saying is that for all values of x, there's some value for y where the biconditional comes out true. And now, because I looked at all of the possible values for x and y and the results for the biconditional, I can just physically check whether this is the case, whether it really is the case that for all values of x, there's some value for y where the biconditional comes out true. And so I look over here for the first value for x, where x equals 1, and I see that there is some value for y where the biconditional is true, namely when y equals 2. So I know that this first case, where x equals 1, makes the biconditional true. When I look over here and I see that x equals 2, and I see that there's some value for y where the biconditional is true, namely when y equals 1, I can also see that it's true down here for this second value of x. Because it's true for all values of x, that there's some value for y for which this biconditional holds, namely this value for y here and this value for y here, for these values of x, then it follows that the biconditional statement with the universal quantifier right out the front is true. So the difference between this case and the last case is that the last case I had the double universal, and the double universal would have forced me to make all of these biconditionals true. With just the universal and the existential, I only need to make it, I need to make it true for all values of x, but I only need to make it true for one of these values of y for each value of x. So I don't need to be all four to be true, I just need one to be true for each value of x. All right, let's look at a third case now, which is slightly different again, and a little bit more complicated still. All right, so what I'm going to do now is I'm just going to make the model complicated again, a little bit more complicated than the previous one. So this time, I'm going to have 3 objects in the domain. And I'm going to have a third predicate, C, and I'm going to have a third object, a third name that names that third object 3. And now I'm going to look at a sentence that's got 3 quantifiers in it. So this sentence is going to be for all x, so actually I'm going to start with the existential this time, for some x, and for all y, and for some z, if ax and by, then cz. All right, so that's my sentence. That last bracket's just not quite sitting on the screen properly, but that's just closing the brackets here. And what I'm trying to test is to see whether this sentence is true as stated. Now, I've got 3 variables in here and I've got 3 objects. And now what I have to do is I have to start by doing that same splitting procedure. There's how many values for x, how many values for y, and how many values for z. And I'm going to end up with a space of combinations that I have to check. So let's start by seeing how that looks. So I'm going to get x equals 1, x equals 2. Those are my 3 possible values for x equals 1, x equals 2, x equals 3. And for each of those, I'm going to have 3 values for y. And then for each of those values of y, I'm going to have 3 values for z. So you can see that as you increase the number of variables and you increase the number of objects inside your domain, this checking procedure, this sort of manual checking procedure, the complicated way, rather than just eyeballing the sentence and trying to work out what it says, gets more and more complicated, gets harder and harder to do. But although that's true, as long as you write out all of the combinations and check each one, you'll be able to come up with the right answer every time. So the trade-off is something like this. With the eyeball checking method, when you just look at it and you try and work out whether it's true or not in your head, it's quicker, but you might not get the right answer every time. In this case, it's when you do the sort of complex, long method, it's going to be more accurate in that you'll get the right answer every time, but it's going to take longer. And you've got to try and work out, for a given case, which one of these you can get away with so that you can work out sort of how to manage your time effectively when you're actually dealing with one of these types of problems. Okay, so I'm going to put in these values for z. So z can equal 1, z can equal 2, z can equal 3, all the way along. pretty hard to see these last ones. But there should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. There should be 27 different combinations based on what values you have for x, what values you have for y, and what values you have for z. Okay, I'm not going to evaluate all of these cases. I'm just going to show you how to evaluate this type of situation by focusing on these top cases. So I'm just going to check for the case when x equals 1. But if you're doing this kind of problem, you're going to have to check it for when x equals 2 and when x equals 3 as well. So I'm just going to get rid of these bottom cases just because it's cluttered and we're not going to be checking those cases. In a moment as well, I'll tell you how you work out how many combinations you should have without writing them all down in the way that I just did. Okay, so I'm just going to check for x equals 1. And now for each of these, I'm going to write out this sentence, the A, the B, and the C part, under the assumption that I've got those values for x, y, and z. So I'm going to have A1 and B1 arrow C1. That's because x equals 1, y equals 1, and z equals 1, so it's A1 and B1 arrow C1. And then next is A1 and B1 arrow C2, then A1 and B1 arrow C3, and then for continuing down, we go A1 and B. Now we get B2 because Y has shifted to being 2. We're on this second track down here. Arrow C1, we're back to start. We've sort of gone back to the start of the Z values to go back to Z being 1, 2, or 3. So A1 and B2 arrow C2, and then A1 and B2 arrow C3, and then the final set of combinations. Remember, I'm just taking one value for x here. There were 27 overall. So there's when there's 3 values of x, you've got 27 combinations in this situation. Because I'm just dealing with one value of x, I'm just going to have a third of those combinations. So I should have 9 combinations here to deal with. The last 3 combinations are when A equals 1, B equals 3, C equals 1, then A, 1, and B, 3, and C, 2, and then A, 1, and B, 3, arrow C, 3, like that. Okay, so there's the 9 combinations. And now I've got to work out whether all of these conditionals are true. That B there's a bit messy, I'll just fix that up. We work out whether all these combinations are true, but I'm just going to do that in exactly the same way I was doing it for the last couple of cases. So I'm just going to work through these values for A, B, and C. When I've got 1 inside the extension of A, I mark it as true. When I've got 2 inside the extension of B, I mark it as true. When I've got 3 inside the extension of C, I mark it as true. But for all the other cases, I mark it as false. Now I'm going to use the shortcut that I used last time of looking for the true cases to help me through. So when I know that 1 is in the extension of A, so whenever I've got A1, I'm going to put that down as true. Now, because x is equal to 1, I know that the A part of all of these sentences is true. So I'm just going to put put T's all along this section for the A part. So that's 9 T's that I'm going to have. Okay, for all of those A values. And then, whenever I see that B equals 2, I'm going to put in trues for those because I know that 2 is inside the extension of B. So I've got those 3 cases there. I'm going to put trues in for those. For all the other cases of B, I can put false because I know that there's nothing else inside the extension of B. So that helps me to work that out pretty quickly. So I've actually only got 3 cases where both A and B are true here. So the last thing I'm going to do is the C, and I know that C is true when you've got a 3 inside the extension of C, so whenever I've got that, I'm going to put in true, and then I'm going to put false for all the other cases, because nothing else is inside the extension of C. And now, given this information, I'm going to evaluate these conditionals. And what the conditional is really a conjunction inside the antecedent of the conditional, inside the left-hand part, with the C part on the right-hand side. So I've got to see whether the antecedent is true, and if the antecedent is true, I've then got to test the consequent. So for 6 of the 9 conjunctions that I've got here, I know that they're false because I've got a value for A where it's true and a value for B where it's false. Namely, when A equals 1 and B equals 1, it's false. When A equals 1 and B equals 1, it's false. So whenever I've got B equaling anything other than 2, I know that it's false. So I've got those 6 conditionals. The antecedent, the conjunction on the left-hand side, is false. And I know that because I've got B being false, I've got one side of that conjunction being false. And all I'm using at this point is just the same truth table semantics for the conjunction. And now because that antecedent for 6 of those conditionals is false, I know that 6 of those conditionals are true because the statement, the conditional statement is true whenever the thing on the left-hand side is false. Now, that leaves me with 3 last conditionals to check. For these 3 last conditionals, I know that the antecedent is true because the conjunction of A and B is true. It's true on both sides. Now, I look at the right-hand side. When C equals 1, the conditional is false because the antecedent is true and the consequence false. I've got the first thing, but I don't have the second thing. And when C equals 2, the same thing happens because I've got the first thing, A and B. The conjunction is true, but the thing on the right is false. And then for this last case, A and B are true, and the consequent is true, so the entire conditional is true. Okay, so what that means is I tested 9 conditionals, and of those 9 conditionals, 7 of them turned out to be true, and 2 of them turned out to be false. Okay, so let's come back to this statement up here and see if we've actually got enough information to work out whether or not this is true yet. Remember, there were 2 other values for x that I needed to check. And I would have to go through this same procedure for those other 2 values for x if I'm checking all of the possible combinations. Fortunately, I should be able to work out whether or not this is true just based on the information I've got here, so I'm not going to have to chew through all 27 combinations, but sometimes you might. And so you've got to be careful about when you stop, so make sure you don't stop too early, and you've got to be aware of the structure of this, of what it's saying. Okay, so what this is saying is there's some value of x such that for all values of y, there's some value of z, which means that I need it to be the case for one of these, I needed that to be true for one of those values of x that was there, and I needed it to then be true for all of the values of y, and then to be true for some value of z. And now, if you look back at the model that I just produced and the evaluation, you'll see that there was in fact some value for one case where when x equaled 1, all of the values for y made the conditional true. And that was actually any case where y was equaling something that was making the conjunction, the bit on the left-hand side of that conditional, false, because then the conditional was coming out true. And that was then true for some value of z. So we needed to be true that for all values of y, there was some value of z that was making that conditional true. And in fact, we have some value for x, where for all values of y and for all values of z, that conditional was coming out true because there was 8 out of those 7 out of those 9 conditionals where it was coming out true. So it turned out that statement, the one that we were interested in, this statement here, ax and by, therefore cz, this statement was true because there was some value for x. We had x equal 1, where we had all 3 values for y. And for each of those values, for one of those cases, namely when y was equal to 1 or when y was equal to 3, the conditionals that came out were true regardless of whether z was true or not. And so that meant that there is some value for x such that for all of these values for y, namely when y equals 1, or y equals 2 or y equals 3, there was some value for z where it made it true. Now we could see that by looking at the 1 and the 3. Those were the easy cases. When y equals 1 and y equals 3, all of the conditionals turned out to be true because the antecedent was false. When y equals 2, we had 2 of the conditionals fail, and that was because when b equals 2, this conjunction here turns out to be true in the model that we had, but there was some values for z where it turned out to be false. But fortunately, we didn't need to be true for every value of z, we just needed it to be true for some value of z, and we had some value for z when y equaled 2, namely when z equaled 3, that was going to make this true. So there was always some value for z for any value of y that made this true. So we did have it the case that there was some value of x such that for all values of y, there was always some value for z that we could plug in that would make this sentence true. And we could see that just by going through the combinations and testing each one. Fortunately, I only had to go through 9 of the combinations in order to work this out, but sometimes you might need to go through more than that in order to determine whether it's true. All right, so as you can see, things can get quite complicated quite quickly when you're adding more objects and more variables. So in general, there's a function here that describes how many combinations you will need to check in order to work out whether or not a sentence is true. And the function is this, where O is the number of objects and N is the number of variables, the number of combinations is equal to the number of objects to the power of N. So if you've got a domain of 2 objects, and you've got a sentence with x, y, and z in it, then you've got to check 2 to the power of 3 combinations, namely 2 times 2 times 2, which equals 8. And that was, in fact, the number of combinations we had to check when we looked at a case exactly like this, when we had 3 variables, but we only had 2 objects in the domain. Okay, so that's how many combinations you might have to check. And so if you've got lots of objects in the domain and lots of variables, you might end up having to check hundreds or thousands of different combinations, which can make it very difficult, in fact, to work out, given a model, whether or not a sentence is true. Given that, you're going to be interested in shortcuts for working out ways to do this more effectively and more efficiently. One of the shortcuts that I've already mentioned is to try and get your eye in. So you work out when what the sentence is saying and whether or not it's true or false given the model that you're interested in. You use that rough and ready checking method. And if you can train that up to get that quite efficient, then you'll be able to get the answer most of the time. The other way is to keep in mind the truth table's semantics for the conditional and the disjunction and the conjunction. And remember that with the conditional, it's true when the thing on the left is false or the thing on the right is true. For the conjunction, that's true when both sides are true and in no other situation. And for the disjunction, it only takes one side to be true to make the disjunction true, and for the biconditional, the 2 sides have to agree. And what you can do is when you might have 100 options to check, but you might see very quickly that, say, the antecedent of 80 of those options for a conditional that you're having to check turns out to be false, making 80 of those conditionals true, which means you only have to check 20 of them. Or you might find that you've got 90 options and then only 89 of them that you actually have to check because most of them are coming out to be true because of one of these features of these propositional connectives. So there are sort of two things that you need to keep in mind here. One of them is that the number of combinations obeys this kind of function. So if you're in doubt about how many things you should be writing down, how many splits you should do, when you write x, y, and z, it's the number of objects, the power of number of variables, it's the number of combinations you need. And if you need some shortcut heuristics, these are the shortcut heuristics. Keep in mind the truth tables for each of these so that you can apply those to whittle down some of the conditionals or conjunctions or disjunctions that you're dealing with when you're having to check those combinations. In some cases, there's just no other way to do these except by going the long way. But at least you've got a method, you've got a process that if you follow precisely, you check each value of x, each value of y, each value of z, you look at all the combinations and then you make a judgment about the sentence based on that checking procedure, you'll be able to get the right account of whether the sentence is true or false against the model. But that said, the process can be quite difficult and it can require a lot of just sitting there chewing through the combination. So keeping an eye on these shortcuts is a really valuable thing. Okay, I hope that helps you to evaluate things against models. Basic idea is that when you've got a model and you've got a sentence, you look at the possible things that the variables could take from the domain, the possible values that it could take, and you look at each of those values in order to work out whether or not each instance of the sentence is true under the sort of various suppositions for the values for the variables. And then, based on what the sentence is trying to say, whether it's universals or existentials that are governing the sentence, work out whether or not the sentence is true based on how that space of combinations that you've gone through has actually ended up looking. Okay, thank you very much, and I'll talk to you next time.